today we're going to talk about linear combinations and spanning sets in R2. So a linear combination is an important concept in linear algebra. It's defined as the sum of non-zero multiples of two or more vectors. However, in R2, we're only concerned with two vectors forming a linear combination. So what's a linear combination? It's basically, if you're given a set of vectors, what other vectors can you create by adding or subtracting scalar multiples of those vectors? So any arbitrary scalar vectors. So mathematically, we can express a linear combination as vector z is equal to a, which is a scalar, times vector x plus b, another scalar, times vector y. So in this case, we would say that z is expressed as a linear combination of x and y. Okay, now as an example, we want to show that vector x, which is 423, can be written as a linear combination of either sets of vectors. So your first set is negative 1, 4 and 2, 5. Second set is 0.10 and negative 2, 1. So let's split them up. We're going to do part A, so that's the first set, which is negative 1, 4. So let's say, let's call it vector M be negative 1, 4, and vector N be 2, 5. Okay, so if we want to write x as a linear combination of these vectors, our equation would be x is equal to, a is going to be a scalar quantity times vector m plus b vector n. And if we just fill this in, we would get 423, which is vector x, is equal to a times this vector here plus b and then vector n. Alternatively, if you wanted to write this in matrix notation, you could write 423 is equal to a negative 1, 4 plus b 2, 5. Now what do I want to do is split them up so we have a linear system of equation. So 4 is equal to, in this case, negative a plus 2b. And then for your y values, you have 23 is equal to 4a plus 5b. So now you have two equations, two unknowns. We can either use substitution or elimination to solve for our scalar quantities. I'm going to start with first equation here, solve for a. So I'm just going to isolate a and bring everything to the other side, multiply by a negative, so I get negative 4 plus 2b. And then with that, I'm going to bring it into this equation. So 23 is equal to 4. A is negative 4 plus 2b plus 5b. And now you have an equation that's all b's. That's what you want, one equation with one variable, so now we can solve for b. So when we expand this, we get negative 16 plus 8b plus 5b, and that gives us 39 is equal to 13b. And b is equal to 3. So now take b, bring that back up here, and sub it into this equation so we can solve for a. Times 3, which gives us a is equal to 2. So now we have our value for a, we have our value for b for this particular linear combination, and so we can express our final linear combination as vector x, which is 423, is equal to 2 times negative 1, 4, plus 3, which is b, and then vector n, so 2, 5. And alternatively, you can just write this in matrix form. If you multiply these out, you'll notice that they're equal, so left-hand side should equal right-hand side. Okay, so in case you didn't believe me the first time that this can work with another set of vectors, we're going to use our second set of vectors. We're going to let m be equal to 1, 0, and vector n be equal to negative 2, 1. And we want to find a linear combination for vector x. So vector x is the same value, 423, and x is equal to a times vector m, so scalar quantity times m, plus b n. And so we're using the same vector x, just m and n are different this time. So setting it up in the same way, this is going to be 1, 0, plus b, negative 2, 1. And alternatively, if you wanted to write this as a matrix, it is equal to a, 1, 0, plus b, negative 2, 1. And these are equivalent. So now let's split it up into our two equations. And so we have 4 is equal to, just read it across, a minus 2b. And on the other side, it's 23 is equal to, I guess, 0a plus b. Obviously, I want to start on this side because b is equal to 23. It's pretty simple. We could just take that, sub it into here. So now a is equal to 4 plus 2b, which is going to be 4 plus 2 times 23. And so a is equal to 50. So b is equal to 23, a is equal to 50. So our linear combination can be written as 423 is equal to value a, so 50, 1, 0 plus 23, which is b, and vector n, or and again, these are equivalent. And if you wanted to verify, you can multiply them through and make sure that your left side is equal to your right side. It should, because that's how we found it. So now let's talk about spanning sets. A set of two vectors forms a spanning set for R2 if every vector in R2 can be written as a linear combination of these two vectors. In other words, the spanning set can be used to write any vector in R2 with the application of appropriate scalars. So essentially, any two vectors, non-zero vectors, can be written as a linear combination in 2D. So in R2, it's possible to take any pair of non-collinear, non-parallel vectors as a spanning set, provided that 0, 0 is not one of the two vectors. So it has to exist and it can't be collinear. So let's talk about that before we go on to our example. Okay, so I'm just going to create two vectors here. So this is going to be our vector A, and this is going to be vector B. So these are just any two arbitrary vectors, and I'm going to add up A and B. So tail to tip, that's your vector B. Now your linear combination of A and B will get you, if I did A plus B, this vector right here. So this is just A plus B. Now say I multiplied A by 2. So now I'm getting 2A. And I'm multiplying B by half. So I just made it shorter by half. Now we get this vector right here. So this is 2A plus half B. So I can scale these values any way. Like now I can say negative A. And I'm just picking random values here. So I'm going to add that to, let's say, let's just go with B. And your resultant vector is going to be this. So essentially what I'm showing you here is that I can create any path, that's any possible path with any combination, any linear combination of these two vectors. So here's a few more in case you're not a believer yet. And as you can begin to see, the number of linear combinations that you can create with these two vectors is infinite. So now let's go back to our rule. In R2, it is possible to take any pair of non-collinear, non-parallel vectors as a spanning set, meaning you can create infinite number of linear combinations with them, provided that 0, 0 is not one of the two vectors. So we want to show that the set of vectors 2, 3, and 4, 6 does not span R2. Immediately when we look at this, we know that we can see that 2, 3, and 4, 6 are collinear because 4, 6 is just a multiple of 2, 3. So now we just want to show why this isn't going to work. Okay, I'm going to let vector M be 2, 3, just like in our previous example, and N is going to be 4, 6. So let's try to make a linear combination out of these vectors. So we're going to say xy is equal to am plus bn. And so xy would be, in this case, 2, 3 plus b, 4, 6. And if we split these up into our equation, and actually just to stay consistent, let's write this in matrix form as well. So that's just going to be 2, 3 plus b, 4, 6. And so let's split these up into our x equations and then our y equations. So x is equal to 2a plus 4b. And for your y, you're going to have y is equal to 3a plus 6b. Okay, so now let's isolate for a. And so we have x minus 4b is equal to 2a. And so divide by 2. A is equal to half x minus 2b. And for y, I'm just going to sub this back into here. So now we have 3 half x minus 2b plus 6b. And so that gives us 3 over 2x minus 6b plus 6b. These are going to cancel out, so you get 0. And so we get y is equal to 3 over 2x. Now, just looking at this, we can see that x is a multiple of y, but not a linear combination. If you try to add sections of this vector to from x to y, you would notice that it would just be along the same line, right? So you're just adding and subtracting components of the same line. So therefore, this is not a linear combination and does not span R2. Okay, so now we want to show that the set of vectors 2, 1, and -3, -1 is a spanning set for R2. Just looking at them, they look okay. They don't seem collinear, and there's no 0, 0, so I feel like this can work. So now let's just set it up the same way we've been setting it up. Let m be 2, 1, and n is -3, -1. Now let's set up our linear combination. So xy is equal to a 2, 1. I'm just going to skip that first step. B -3, -1. I'm going to write it as a matrix. Now separate your equations. You get x is equal to 2a minus 3b, and y is equal to a minus b. Okay, now easiest to work from the side right here. We can solve for a. I'm just going to solve for a here, so you get y plus b. Take that, sub it into this. So x is equal to 2 y plus b minus 3b. Okay, now expand this to b minus 3b. X is 2y minus b. And b is equal to 2y minus x. Now let's take this and sub it into our a equation. So y plus 2y minus x. So a is equal to 3y minus x. And since a and b are unique here, you know that m and n are going to be spanning sets of R2. And now for some linear combination and spanning sets in R3. When we're working with linear combinations in R3, we're concerned with 3 vectors forming a linear combination instead of 2. So in other words, a linear combination in R3 is formed when 3 vectors are multiplied by any arbitrary scalars and then added up. So in this example, we want to show that the vector 2, 3, -5 can be written as a linear combination of I, j, and k. So first step, we just want to write this in unit vector form. So you're going to have a times your unit vector I plus b unit vector j plus c unit vector k. And so 2, 3, -5 can be written as this unit vector I would be 1, 0, 0, because that's essentially what it is. And then b would be 0, 1, 0, that's your j vector. And times c, that's your scalar, it's going to be 0, 0, 1. So now I'm just taking the unit vectors and translating them to, I guess, coordinates. And we can now, we have our linear combination and separate them into our, I guess now, 3 equations. So 2 is equal to a plus 0b plus 0c. So in this case, a is equal to 2, obviously. For our y value, we have 3 is equal to 0a plus b, sorry, it's a really bad 0, plus 0c. So then 3 is equal to b. And our third equation is, I'll just do it in the middle here, negative 5 is equal to 0a plus 0b plus c. So obviously negative 5 is equal to c. And I know this seems really intuitive. You could see this right away. I'm just breaking it down so you can start thinking of it in this form. So this is going to be 2i plus 3j minus 5k, which I'm sure if you looked at that vector you immediately saw, but good idea to just start thinking about your unit vectors in terms of coordinates. So a spanning set in R3 is any pair of non-zero vectors that will span a plane in R3, so in 3 dimensions. So given the two vectors, A is negative 1, negative 2, 1, and B is 3, negative 1, 1, does the vector C, negative 9, negative 4, 1, lie on the plane determined by A and B? So A and B are forming our plane, and we want to see if C lies on it. Okay, so the way to determine that, if C lies on the plane A and B, we should be able to write it as a linear combination. So let's do that. So C is equal to scalar m times vector A plus n vector B. So now we've set up our linear combination, and we're going to split up our equations. So here we have equation 1, this is for your x values, equation 2 for your y values, and 3 for your z values. So looking at these equations, I feel like I'm going to work with equation 3 because it's the simplest to isolate for a variable. We can isolate for m. Doesn't matter what you isolate for. So it's going to be 1 minus n. And now take that, and we can substitute that into equation 2 because it's right there. So it's going to be negative 4 is equal to 2, negative 2, and then m is 1 minus n. So that gives us negative 2 plus 2n minus n, and I'm just going to do this in one step. N is equal to negative 2. Okay, now let's take this value of n, sub into equation 3. So m is equal to 1 minus 2, and that gives us 3. So m is equal to 3, n is equal to 2. So we had 3 equations, 2 variables, so that's more than enough information to solve for your variables. Now to write this as a linear combination, we can say that vector C is equal to 3a minus 2b. Those are the values for m and n. And so since C can be written as a linear combination of a and b, we can say that a and b span the plane that C lies in. Okay, for our last example, determine the value of x such that the points a, which is negative 1, 3, 4, and b, negative 2, 3, 1, and c, negative 5, 6, x, lie on a plane which contains the origin. So let's write this as a linear combination. And then now to fill in your values, vector OC is just negative 5, 6, x, and x is what we're looking for. Your scalar m, and OA is going to be negative 1, 3, 4, plus n, and OB is going to be negative 2, 3, negative 1. Okay, so now I'm ready to split up my equations into 3 equations. So x, y, z. Okay, so looking at equation 1, I'm just going to isolate for m. So in equation 1, m is equal to 5 minus 2n. And looking at equation 2, I'm going to substitute these values. So 6 is equal to, let's just leave equation 3 for now. So 3m, which is 5 minus 2n, plus 3n, so we're just using substitution here. So you get 6 is equal to 15 minus 6n plus 3n. You get negative 9 is equal to negative 3n, and n is equal to 3. Take this, bring it back up here, and m is equal to 5 minus 2 times 3, and that gives you negative 1. Now, the reason I wanted to solve for both is because in equation 3, you have m and n as values, as variables. So once you've solved, again, remember you only need 2 equations to solve for 2 variables. So if we have 3 equations, that's more than enough information. And so we can substitute our m and n values. So we have negative 1 here, minus 3, which gives us x is equal to negative 7. So therefore, if x equals negative 7, a, b, and c all lie on the same plane and contain the origin. And the reason for this is because it can be written as a linear combination. This video was filmed in front of a live studio audience. And now a word from our live studio audience.
Thank you, Miss Weiss. I loved learning about linear combinations and spanning sets. I never realized how cool vectors were. Vectors might be almost as amazing as science.